Ranking data involves converting a set of raw values into their relative positions within the dataset. This is a crucial step in performing rank correlation analysis. Rankings represent the relative position of each value in a dataset. We typically rank from smallest to largest, known as ascending order, or from largest to smallest, known as descending order. In ascending ranking, we assign rank 1 to the smallest value, rank 2 to the second smallest, and so on. Here, Charlie has the lowest score of 42, so gets rank 1, while David with 95 gets the highest rank of 6. Alternatively, in descending ranking, we assign rank 1 to the largest value. This reverses our ranking, so David now has rank 1 and Charlie has rank 6. Consistency is crucial. You must use either ascending or descending rankings for all variables in your analysis. A common challenge in ranking data is handling ties when two or more values are identical. Let's look at this example with several tied scores. To handle ties, we assign the average rank to tied values. Notice that Bianca and Diana both have scores of 92, so they share ranks 5 and 6, receiving an average rank of 5.5. Similarly, Carlos and Felix, with scores of 78, share ranks 3 and 4, receiving an average rank of 3.5. Ranking data is critical for correlation analysis because it makes the analysis resistant to outliers, removes the effects of different scales and units, captures monotonic relationships, not just linear ones, and works well with ordinal data and non-normal distributions. Now that we understand how to properly rank data, in the next section, we'll learn how to calculate Spearman's rank correlation coefficient using these ranks. Spearman's rank correlation coefficient, represented by the Greek letter rho, measures the strength and direction of monotonic relationships between ranked variables. The formula for Spearman's rho is given by rho equals 1 minus 6 times the sum of d squared divided by n times quantity n squared minus 1. Let's understand the components of this formula. Rho represents the Spearman's rank correlation coefficient, the value we're calculating. D is the difference between the ranks for each paired observation. N is the total number of observations or data pairs in our sample. Let's work through an example to see how Spearman's rank correlation is calculated. First, we convert our raw data to ranks. For each variable, we assign rank 1 to the lowest value, rank 2 to the second lowest, and so on. Next, we calculate the difference between ranks for each observation, square these differences, and find their sum. Now we apply the formula. With 5 observations and a sum of d squared equal to 0, we get rho equals 1 minus 6 times 0 divided by 5 times 24, which equals 1. In our example, the raw data already shows a perfect monotonic relationship, as students who studied more hours scored higher on the test. When we convert to ranks, we can see this perfect relationship even more clearly, with all points falling precisely on a straight line. Let's interpret what different values of rho mean. A rho value of positive 1 indicates a perfect positive correlation, where ranks match exactly. A rho value of negative 1 indicates a perfect negative correlation, where ranks are exactly opposite. A rho value of 0 indicates no correlation between the ranks. Let's visualize this on a scale from negative 1 to positive 1. Our example resulted in a perfect positive correlation with rho equal to 1. Let's summarize the key points about Spearman's rank correlation coefficient. Kendall's tau is another important rank correlation coefficient used to measure the association between two variables. Unlike Pearson's correlation that measures linear relationships, Kendall's tau works with ranked data to assess if two variables change together. The key concept is counting pairs of observations and determining if they change in the same direction or opposite directions. Let's use a simple example with students' math and science scores to understand concordant and discordant pairs. A concordant pair is when the order of two observations is the same for both variables. For example, student A scored higher than student B in both math and science. This makes AB a concordant pair. A discordant pair is when the order of two observations is reversed between the two variables. For example, student B scored higher than student D in math, but student D scored higher than student B in science. This makes BD a discordant pair. The formula for Kendall's tau is relatively straightforward. It's the difference between concordant and discordant pairs divided by the total number of possible pairs. In this formula, C represents the number of concordant pairs, while D represents the number of discordant pairs. N is the number of observations, and the denominator represents the total number of possible pairs, which equals n times n minus 1 divided by 2. Like other correlation coefficients, Kendall's tau ranges from -1, indicating perfect disagreement, to +1, indicating perfect agreement. Let's compare Kendall's tau with Spearman's rank correlation coefficient. When it comes to handling ties, Kendall's tau requires a special adjustment to both the numerator and denominator of the formula. The adjusted formula accounts for ties by modifying the denominator based on the number of ties in each variable. Kendall's tau is particularly sensitive to different types of relationships between variables. For linear relationships, both Kendall's tau and Spearman's rho will be close to +1. Kendall's tau excels at detecting monotonic relationships, where variables consistently increase or decrease together, even if not linearly. However, for non-monotonic relationships like sinusoidal patterns, Kendall's tau will be close to 0, indicating no consistent association. Kendall's tau offers several advantages. It's more robust to outliers than Spearman's rho, has a direct probabilistic interpretation, and is often preferred for small sample sizes. Let's calculate rank correlation coefficients step by step using a practical example. Here we have test scores and heights for 6 students. We'll work through this example in 3 main steps. First, we'll convert the raw data to ranks. Then we'll calculate Spearman's rank correlation. Finally, we'll calculate Kendall's tau. The first step is to convert our raw data to ranks. For each variable, we rank the values from lowest to highest. The smallest value gets rank 1, the next smallest gets rank 2, and so on. If there are ties, we assign the average of the ranks they would have received. For Spearman's rank correlation, we need to find the differences between ranks and square them. We use the formula where R sub s equals 1 minus 6 times the sum of d squared divided by n times n squared minus 1. First, we calculate the difference between each pair of ranks. Then we square these differences and sum them up, plugging these values into the formula. For our data with 6 students, we get a Spearman's rank correlation of 0.943, indicating a very strong positive correlation. For Kendall's tau, we need to count concordant and discordant pairs. Concordant pairs are when the ranks of both variables increase or decrease together. Discordant pairs are when one rank increases while the other decreases. We analyze all possible pairs of observations and count them. In our dataset, we have 14 concordant pairs and 1 discordant pair. Using the formula, tau equals the difference between concordant and discordant pairs, divided by the total number of possible pairs. This gives us a Kendall's tau of 0.867, also indicating a strong positive correlation. Comparing our results, Spearman's correlation is 0.943 and Kendall's tau is 0.867. Both values indicate a strong positive correlation between the test scores and heights in our dataset. Kendall's tau is often lower in magnitude than Spearman's correlation, but both tell us that as test scores increase, heights tend to increase as well. Rank correlation coefficients range from +1 to -1, with specific values having distinct interpretations. A value of +1 indicates perfect positive correlation, where ranks increase together perfectly. 0 indicates no relationship between the variables, with ranks showing no consistent pattern. -1 shows perfect negative correlation, whereas one rank increases, the other decreases perfectly. When interpreting rank correlation values, we commonly use guidelines to classify correlation strength. Correlations near 0 are very weak, while those above 0.8 are considered very strong. However, interpreting correlation values requires considering the context of your research. For example, a correlation of 0.3 might be considered weak in physics, but moderate in psychology or significant in epidemiology. When comparing correlation methods, it's crucial to understand which is most appropriate for your specific data and research question. Let's compare Pearson's correlation with rank-based methods like Spearman and Kendall's tau. Each is optimized for different data types and relationships. Let's explore 4 key scenarios where rank correlation methods are typically preferred over Pearson's correlation. Scenario 1. When working with ordinal data, such as customer satisfaction ratings, rank correlation is more appropriate. These methods properly handle the ordered but non-interval nature of the data. Scenario 2. When your data shows a relationship that consistently increases or decreases, but not in a straight line. Rank correlation captures the monotonic relationship perfectly, while Pearson may underestimate the strength of association. Scenario 3. When your dataset contains outliers. Rank correlation is less sensitive to extreme values because it only considers the order of the data, not their actual values. Scenario 4. When your data violates assumptions of normality. Pearson's correlation assumes normally distributed variables, while rank correlation methods are distribution-free and don't require this assumption. When deciding which correlation method to use, ask yourself these 4 questions. If you answer yes to any of them, rank correlation is likely more appropriate than Pearson's correlation. Let's look at a real-world example comparing hours studied and exam performance. When analyzing ranked outcomes, Spearman's correlation perfectly captures the relationship, while Pearson would only be appropriate for the raw scores. Rank correlation has numerous real-world applications across various fields. We'll explore 4 key fields where rank correlation methods are widely applied. In finance, rank correlation helps analyze relationships between stock performances over different time periods. We can rank stocks based on their returns. Here are the rankings for year 1, and here are the rankings for year 2. We can then calculate the rank correlation to see if performance is consistent over time. A Spearman rank correlation of -0.4 indicates a moderate negative correlation, suggesting stocks that performed well in year 1 tended to perform worse in year 2. In education, rank correlation helps analyze relationships between different test scores or assessments. Here we have data comparing students' math and science scores. Each point represents one student. Calculating Spearman's rank correlation gives us a value of 0.93, indicating a very strong positive correlation between math and science scores. This type of analysis helps in curriculum development, identifying student strengths and weaknesses, and validating assessment tools. In medicine, rank correlation helps researchers study relationships between disease severity and various biomarkers. Here's an example of patient data showing disease severity levels and corresponding biomarker measurements. We can rank patients by their disease severity, with lower ranks representing milder conditions. Similarly, we rank biomarker levels from lowest to highest. Calculating Kendall's tau gives us a value of 0.87, indicating a strong association between disease severity and biomarker levels. In social sciences, rank correlation is commonly used to analyze survey data and preference rankings. Here we have data showing how 2 different demographic groups rank various social issues by importance. The Spearman rank correlation of -0.7 reveals a strong negative correlation, indicating these groups have substantially different priorities. To summarize, rank correlation methods have powerful applications across multiple disciplines, from finance and education to medicine and social sciences. They provide robust tools for analyzing relationships in data, especially when dealing with rankings, ordinal data, or when the relationship between variables may not be linear. Let's examine common pitfalls and limitations when using rank correlation methods. There are 4 critical limitations to be aware of when working with rank correlation. The first major pitfall is assuming correlation implies causation. High correlation between variables doesn't mean one causes the other. For example, ice cream sales and drowning incidents show a strong rank correlation, but this doesn't mean ice cream causes drownings. Both are actually influenced by a third variable, summer temperature. The second pitfall is ignoring ties in your data. When multiple observations share the same value, they must be assigned the average of their positions. Notice how items B and C have tide scores of 87 and D and E are tied at 76. Assigning them naive sequential ranks would distort your correlation calculations. Instead, tied values should receive the average of their positions. The third pitfall is applying rank correlation to inappropriate data types. Rank correlation is designed for ordinal data with meaningful rankings. Rank correlation is particularly problematic for non-monotonic relationships, like this U-shaped curve, where the relationship can't be captured by simple ranking. The fourth pitfall is misinterpreting rank correlation results. There are several common ways analysts can draw incorrect conclusions. Small correlations can be meaningful in certain fields, while large correlations don't prove causation. Also, the statistical significance of any correlation coefficient depends heavily on sample size. To avoid these common pitfalls, follow these best practices when conducting rank correlation analysis. Understanding these limitations helps ensure proper application and interpretation of rank correlation indices in research and analysis.